All right, hello everyone. We're going to do another Leetcode question today. I'm going to be doing this as a mock interview. You probably know the drill by now. If you're interested in following along, we're going to do an easy question. I'll choose one at random, and I'll have the link in the description as well as timestamps for the different sections of this interview. Usually this takes around half an hour if we're lucky, and I kind of try to talk about what I'm thinking about during the interview rather than just writing up the solution, which in a perfect world, the actual code should only take a couple minutes, but it's really about how you get there that is the important thing in an interview. Or at least that's my thoughts on it. So let's choose one at random and see what we get. Starting the timer. Hey, it's the Fibonacci number. Haven't seen that one before. All right, so the Fibonacci number, commonly denoted as f of n, forms a sequence, the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. That is, starting at f of 0 is 0, f of 1 is 1, those are given, and then from then on, the next one is the sum of the previous two, for all n greater than 1. Cool. And they just want us to solve for this, and the constraints in this case is from 0 to 30. Questions I'd have is, do you want all of the values, or do you want just for a specific value? So it looks like the way they're asking is they want it for just a specific n, and they don't care about any of the previous ones. And it's not for multiple calls to this, so there's some approaches here. So step one, the most basic approach, approach one is recursive. This is the most classic way to solve this kind of problem. You create a function called Fibonacci of n, which they have there, and then you just return the fib of n minus 1 plus the fib of n minus 2. I think that's how it works anyway, yeah. In fact, that's what they give us right here in the thing. And you have a special case. If n is less than or equal to 1, return n for 0 and 1. And that's really the whole function. So might as well just write this up real quick right now, just so we're on the same page. Let me bring this down, remove all these extra spaces. So that's our first approach. So how bad is this function? Well, for every call to n, you're making 2 more calls. And you're doing that going backwards until you reach the first value. So if we were to just do for 1, let's just ignore the second one. For n, we would then call for n minus 1, then n minus 2, all the way back to n. So you would be doing n calls for O of n, for a single one, but you're actually doing 2 of them for n minus 1 and n minus 2. And I really hope I haven't completely forgotten about this. I was trying to figure out this is like a 2 to the n sort of thing, but I don't think it expands that quickly. I think this still ends up being for every... Well, no, it is. It's not n squared because you're not... It is 2 to the n, I believe. So every time you make a call, you have that value, and then you're calling something twice. You're calling it twice. And then for those, each of them, you're calling them twice, and so on. So it's doubling every single time, which is 2 to the power for... And it goes on until you reach n equals 0 or 1. So it basically happens n times. So you get 2 to the power of n, which is... very, very slow. And in terms of space, you're using up quite a lot of space also, because you're storing all of this in the stack memory. Even though technically the function doesn't have anything in there. I guess you could say in the worst case, you're also going 2 to the n. I might be wrong about this, TBD. Either way, this is one way to solve this problem. I think this technically works and would be valid. N of 2 would be n of 1 plus n of 0, and n of 1 and 0 are just 1 and 0, so n of 2 is 1 plus 0, which is just 1 also, which I believe is correct. Yep, example 1. So the reason that's bad is, as we just described, you're doing this multiple times, and you're noticing, you might not notice here, but you'll notice here at least for n of 3, you're making calls that also make calls that are repeated. So n of 2 is getting n of f1 plus f0. So let me just write that out. F of 3 is equal to f of 2 plus f of 1, which is equal to f of 2 is equal to f of 1 plus f of 0 plus f of 1. And that gives you your, 1 plus 0 plus 1, which equals 1 plus 1, which equals 2, which is the correct answer. But we've called f of 1 twice here. So there's a couple ways we could avoid doing that. Either the simplest thing is something called memoization. And you just store, and in fact, I think Python provides, like you can do some sort of import memoize from somewhere, and then you just add a decorator. Oh, sorry, don't look at all that. But you can add a decorator to the function call, and it'll check if it's already called that function before, and then use that value instead of rerunning the function call for iterations. Because right now for f of 3, this doesn't matter too much. It only happened twice. But as you go up to f of 4, you're starting to do this more and more times. And as the number gets big enough, you're starting to do this 2 to the n times. So memoize is one way you can resolve this. And that would bring it back down to a O of n type time complexity. The space is still this 2 of n, or n space complexity, because now you only store it for each n that you're passing in, and there'll only be up to n of them. That's nice. The interviewer might ask you to implement this if you wanted to go this route. So approach 2, recursive plus memoize. So let me just put this back up here. And let's actually make that like that. So I'm just walking our way through all these different examples so we have a sense of what's going on. Another approach is iterative, and this is the one we're probably going to end up implementing. And the idea here is you create an array of length n, and starting from the left, first index, f of 0 essentially, you calculate the fib sequence and go until you hit n. And so this one's quite nice because you don't need to do anything externally. You have a sense of all the storage space. So you have your O of n and O of n solution. Oops, sorry. And we might implement that in a second. Let's quickly think about any other approaches. So can we somehow bring down the amount of space we're storing? And the answer is yes, because you don't actually need, at least I think the answer is yes, iterative and only store a bit. So you only need to store the last 2 values, more or less, time, and ideally O of 1 space, because at any point in the iteration, so like, you started your f of 0, you get to f of 1, f of 3, f of I, is always going to be f of I minus 1 plus f of I minus 2. So you don't actually have to store anything except for these 3 values. Store the last 2 Fibonacci sequences, fib values, and then just shuffle them over as you go. So this one is even more space efficient, probably the most space efficient. Actually, it is. There's a disadvantage to this one versus the third one for a problem outside the scope of this question, which is, what if you're making multiple calls to the Fibonacci number? Let's say you called Fibonacci of 1000, and it returns the value, and you're done. And you've not stored anything, you're good to go. But if you instead store the array and keep that in memory, your O of n, and you'd make multiple calls for n's that are smaller or even larger, you can pre-calculate. You can either just pull it directly from the existing array, or you can expand the array to get to larger n values. And there's even more optimization there where you could start storing, and you can pull in the memoize approach for the first one here, where you store maybe every 100 or every 1,000 or every million Fibonacci values. That way you don't have to recalculate for that range. You just have to get close to it. And there's lots of fun stuff you can kind of talk about with the interviewer about here. I'd say think about it yourself as well. I only just started thinking about this now, but it's kind of fun to think about. So let's start with approach 4, because it is technically the most optimal for time and space for this specific problem. And the way I'd like to do that is the same initialization. Let's just call this fib. And then now if n is less than or equal to 1, we just return the value directly. Otherwise, we start our iterator at equal to 2. And our current value is equal to our index is equal to 2. What I'd like to do is our current value is equal to Fibonacci of index, or let's just keep calling it I actually. I minus 1 plus Fibonacci of I minus 2. And that's kind of what we'd like to do. So let's just say A is equal to 0 and B is equal to 1. And we're not actually going to n minus 1 and n minus 2. These are going to be our last two values. So A plus B. And we might just as well call that C. And then say for I in range 2, which is where we're at. And actually, yeah. For I in range 2 through n, we're going to make C equals to A and B. We throw away A now becomes B now becomes C, and C is unchanged at this point until the next loop. So let's just do a quick check and see if this is correct. And then at the very end, you just return C. And this loop is O of n, and we're only storing O of 1 space. I'm not entirely sure this is exactly right. I might be doing an off by 1. So let's just do a check for Fibonacci of 4. So what do we get? A is equal to 0, B is equal to 1. And we don't need this initialized I anymore. First of all, for n is less than or equal to 1, no. So we continue on past this point. So I is equal to... So we're in our loop. I equals 2. C equals A plus B equals 0 plus 1 equals 1. Then we update A equals B, which is equal to 1. B is equal to C, which is equal to 1. And that's it for that loop. So then we get to the next loop. I equals 3. C equals A plus B. So 1 plus 1 equals 2. So Fibonacci of 3 is 2. That's correct. A gets updated to B. So in this case, A gets updated to B, which is 1. B gets updated to C, which is 2. Okay, and then we do I in range 4. Okay, so we actually need to do one more at this point because we want to include that value. So I equals 4, or Fibonacci of 4. A is equal to 1, B is equal to 2 at this moment. C equals A plus B, so 1 plus 2 equals 3. And A gets updated to B, which is 2, and B gets updated to C, which is 3, but that doesn't matter because we are now finishing the loop and we return C, which is equal to C, 3. And that is correct there. So I think this is right and makes sense. I think at Fibonacci of 2 until n inclusive. And yeah, there we go. And we didn't need to use any sort of temporary variables or anything like that because we're just shuffling everything over. Shuffle A, B, one step forward. Okay, I'd like to see if this function works. We're at about 14 minutes in. Most of the time is spent just talking about all the different approaches, which we can still do after this if we need to. Okay. Trying to think of anything I might be missing here. Edge cases, we're assuming they're valid. We're returning the right value. We're doing a single for loop over the range. Not memoizing. Let's have a look. Sure hope I get this right. All right, the test cases were accepted for the basic ones. Let's see what happens when we get to the larger numbers. And it passed. And so here, I would normally say you don't really need to pay too much attention to speed, but you can clearly see that the recursive approaches would be a lot slower because the Fibonacci expands so quickly. You need to be at least somewhat efficient. And this one is up there for individual Fibonacci values. If there was some sort of memoization and we're doing multiple calls, a different approach might be worth pursuing. But yeah, what a fun classic problem we have here. All right, I'm tempted to talk about how we might do some other extensions. So feel free to drop out here if you're not interested in that part, but let's talk about a couple things here. First off is, what if we pass in multiple n queries at the same time? So this one's a nice question. Like, what if is Fibonacci of a nums, and we want, and nums is a list of ints, and each of them is an n that we want to get an answer for. How could we do this? If we were to apply our original function, like return Fibonacci of n for n in nums, that's one approach, the most brute force you can think of. We've already established that this is a O of n, O of 1 space problem solution. So we're doing, and then let's call this O of k for k numbers. This would become a O of k times n time complexity here, because we're repeating the work for every single one. Still O of 1 space, which is nice. But we could definitely do better. And that kind of gets back to our approach 3, where we've created an array, or even approach 2, where we memoize. So if one could just memoize the fib function. So, we have our fib here of n and so on and so forth. And we just have to add memoize in front of it or implement it ourselves. All of a sudden, this goes from k of n right back down to n. However, we are now increasing this up to n space for the largest number you're going to get, essentially. It is that is what it is. You can change this O of n space for the average case to be smaller if you instead only can change average time complexity from I don't know how to put the symbol. It's like, I think it's theta, or omega is the big one. That's big O of n. I think theta, what the other one is, I don't know, average O. Let's just call it average O for now, because I don't know the symbol. The average O can go from n to something like n divided by 1,000 or something like that. If we only memoize every thousandth Fibonacci value, and you can change that 1,000. You can kind of hyperparameter optimize for whatever number you want. The nice thing about that is now whenever you call an n, it'll iterate backwards until it hits one of these memoized numbers, and then it doesn't have to do any more extra work. So that's one way we can reduce the space complexity down on the average case. Or I guess even, well, it's not the whole case, because you don't know how big n can get. It's technically still infinity for the big O. Or not infinity, but n. It just is a lot smaller in practice. So that's one way to optimize that. The other is creating an array, and I'll kind of talk about that one here. It's kind of like creating a dict. It's like the memoize, but you just store the array one time. So like, let's just say array is like so, and then we have our approach 3. We'll put this in here. Let's copy this over. And then, and we'll actually start it with 0 and 1. And say, if n is greater than the length of array, and this will just be an array we'll initialize outside of the thing, we'll extend array plus the length of array. We'll extend it with zeros times the length of array minus n. So if n is equal to the length of array, we don't need to do anything. If it's greater than n by like 5, we extend the array with a bunch of zeros by the length of the array minus n, or sorry, the n minus the length of array. And then we need to populate those values. And so what we'll do is go for start index is there. And then all we need to do is extend the values of array. So start index through length of the new length of the array. We'll just say array of I is equal to array of I minus 2, 1 plus array of I minus 2. And now we can just return array of n. Zero, 1, we need to actually go to the length of the array plus 1. So yes, because if n is equal to the length of the array, that's too small. We need one more than that. Okay, and this can kind of change as you go, but the intent here is to, if array doesn't have Fibonacci of n, expand array, populate values of array with those, with fib values till we hit n. And this includes the length of array at this point. And just to make this clear, we'll store this original value for the length of the array there and build off of that. Okay. And the nice thing for this one is, it's still O of n and O of n for a single call. For any call actually. But now if we were to call this fib of multiple numbers, and we'll just call this fib multiple, we could call this new one, and it's going to be O of n and O of n without having to use memoize. We've stored this, the memoize has been done by us in this array that's expanding over time. Expanding the array like this is going to be O of, on the order of O of n in the worst case. And it's a one-time thing. And then this is a O of n one-time thing pass. So we end up with our O of n's. All right. That's as much as I can kind of, I mean, we could keep expanding on this with other approaches. This is where like, even a simple question like this, you can kind of probe and ask more questions to make sure that the candidate knows more about the problem and can start thinking about the different approaches. I do really like how there's one nice thing about this kind of question is there's so many different approaches and they're all quite different, even though they have a lot of similarities. Hopefully this was interesting, and if you also went along with this, I'd be interested to know which approach you decided on and which languages you guys use. If you would like to see me do this in another language, maybe I'll consider that. Yeah, I think I've seen it interviewing. Python seems to be like the majority use case. I've seen people use C++. I use C++ in interviews quite often in the robotics field. There's also JavaScript. I think there's Java for some companies, many companies actually. Whichever one feels best for you and you're fastest in. But I will almost always say Python's the best option just for the least amount of syntax and all the extra stuff that comes along with like C and C++. If you get the choice, this one will save you a lot of time in the interview. All right. Have a good day, y'all, and see you again next time.